The objective today is to describe how we go from a high-level programming language to ones and zeros. So here's our table of contents. Before I start that, you should know that maybe a prerequisite for this lesson would be just knowledge of ASCII. I have a video on that for you if you need. Just search Mr. Houghton ASCII, and I'll explain it to you in that. But I think you just really have to know that before going forward. Going forward here, the first thing we'll do is an instructions activity. So basically you can think of this like we're going to use the pencil to represent data. Your input is going to be the motion that is occurring after somebody tells you some directions. So that's a mixture right there. Somebody says something to you, the motion begins. This is the input. The output is the line that will be on the paper. Right here is the high-level language analogy that I'm making. Then I'll go through a speedy history lesson. So this is where we're going from the high-level language down to low-level stuff, or at least that's how I make the transition. I'm going to give a shout out to Ada Lovelace at that time. Then I'll go into some details about how storage works. That is just a key essential element in programming. And then the next thing is just talk about how the keyboard and mice is the thing behind activating the gears in the computer. That is to say, activating the processor. And at the end of the day here, we are not actually using binary. This is what I want you to know. We are using patterns, that is permutations in electricity, to make chain reactions happen. So if I misrepresent anything, please be patient with me. Please forgive me for that misrepresentation. The big goal of this lesson is just to get students comfortable with computer science, because it is a very intimidating field. So in this lesson, I present a lot of tricks and ways to think about computers. That way you just feel more comfortable learning to program them. So let's start the activity, and I just especially want you to do this if you're sitting in my class. I want you to find a partner. Now you'll need a paper and pencil to do this activity. One of you should be the volunteer to close your eyes, and while the other will describe to you how to draw a shape. So maybe the person with the longest hair, you're the one closing your eyes. Now the other person, pick any shape, maybe start with an easy one such as a square, and then try to challenge yourselves. Go with something more complex like a star or a pentagon or a chessboard would be a good one. You may think that's easy because it's just square after square, but whatever you choose, the goal here is for one person to keep their eyes closed the entire time and the other person to give them directions. When you're done with that, here's your think, write, share. Just explain to me, how did it go? Use your imagination if you didn't do the activity to describe to me how you think it would go. And I'd like you to particularly identify what was challenging and how does this relate to programming. Go ahead and predict. So if you said something like giving instructions can be challenging, yes, they can. And we're giving directions to a computer. That's what programming is. And everyone may have a different way of giving instructions. Like everybody around the room may have started with a square, but the way in which you went about giving those instructions to complete that task may have all been very unique. And again, that's why we have all these different types of computer languages, because you can have a unique way of giving the directions. So to further that analogy, the more details you can provide, the better, right? If a programming language can provide a lot of details, it might seem like a better approach, right? Well, those are some of the hardest programming languages to know. I'm talking about like assembly and C. But another thing to think about is the more control the blind person has over their components, that is the hardware, the more control you can have over your hardware, the more precise those instructions can be carried out, and thus maybe the more sophisticated drawing or sophisticated program you can create. That part I felt is particularly confusing right there, so I'm asking you to meditate over it a little bit and to tell me what you think I'm meaning when I say that. Now, before going into the history lesson and moving to the low level, let me just say that there are basically two paradigms to instruction sets. I've used that word incorrectly. An instruction set is either a 32-bit or 64-bit number, and that completely relates to a processor. I have a video about that as well that I highly suggest you watching before watching this video. But there are two types of paradigms for computer languages, for high-level computer languages. You have your procedural ones and you have your object-oriented ones. The procedural one is very step-by-step-ish. So if I'm trying to get my partner to draw this house, I could go step by step. So step 1, draw the bottom line. Step 2, draw a vertical line. Step 3, go draw a line to the right, and so on. And this is probably sounding pretty low level, right? Procedural language would be C. But another approach to programming and giving people directions is object-oriented, like C++ and Python are object-oriented languages. What you can do is say, here's a chimney, so like you could tell your partner to draw the chimney, assuming your partner has the data or the knowledge of basically what a chimney looks like. Now, what are the pros and cons? You can already imagine what those are. We're not going to go too deep into the difference between a procedural and object-oriented language, but just know that these different languages, different high-level languages, are just different approaches to completing similar tasks or the same tasks. So lots of teachers out there will give you all kinds of different analogies of how computer science works or how programming works. I like going with Kung Fu. And I like this lesson because at the end of the day, the user is relying on a chain reaction to be set into motion after some sort of input occurs. So to get some sort of output. This just makes me think of like sorcery or a game of chess at first. I like to tell my students when you're programming, you're controlling electricity with your fingertips. That's like a sorcerer. Or when you're coding or programming, you come up with this big plan first, and then you just need to play the game of chess to get the plan to work out. In programming, you're trying to think several steps ahead. So these are both good analogies. They don't truly represent what I think coding or programming is. I think of it more like Kung Fu. And rather than me just telling you why I think that is, I want to give you a chance to think on that yourself. So at the end of the lesson, maybe you'll understand why I'm saying that. So here's your optional think, write, share. Do you care to take a guess? Why would I say coding is more like Kung Fu? So here's our history lesson, starting at the beginning. God created lightning. I'm just kidding. The first guy to start thinking about binary is a guy named Leibniz, and he essentially invented binary. He's famous for inventing calculus too, I think. And I don't even know if I'm pronouncing his name correctly. After this guy starts thinking about binary, another guy named Francis Bacon turned the alphabet into a binary sequence. So this is basically our ASCII lesson. After Francis Bacon does this, later on you have a guy named Charles Babbage, who built a mechanical calculator called the difference engine. And though this is nothing completely new, the way in which he went about it was. And some of you may have heard of this programming language called Pascal. Well, this guy, or it's the name of a guy, maybe that's where the name of the language came from, was that guy. So a lot of these things are happening, but then you get this guy named George Boole who comes along, and he comes up with an idea that basically leads to logic gates. That is the yes, no, on, off type of stuff we talk about in class. You know, binary. So now that he has a use for binary that can lead to other things, we have the beginning of a computer. And for my students in class, I'm always telling them to play this game on their phones called Circuit Scramble. Because for me, it was an aha moment when I'm looking at these little buttons to push to basically turn on the lights. And when you push the right combination of buttons, you get a screen to light up over here. And what are they going through? Well, these are the logic gates. Now, inside these gates are transistors, so don't think that these are just magical gray rectangles. They are pretty magical. If I turn this light on, the electricity flows through here and will come out the other side because of the way the transistors are ordered inside of this rectangle. So if I have this on and this off and this on, I'm looking at basically 0, 1, 0, 1, and that's the correct combination to get these two on to then get this on. See the chain reaction I'm talking about? And this is one of the earlier levels in the game. Here you get so much more complex. Obviously down here you have 8 bits. So it's just a great game to play so you can kind of more maybe naturally understand how computer science is working and naturally understand what programming languages are ultimately doing. So in the 1930s, you have a group of scientists at AT&T Bell Labs using Boole's ideas. This is the logic gate stuff, and they're using his ideas to get switches to turn on switches, essentially. That's like what I'm talking about here. You switch these two on, and these two switches in the right combination turned on will lead to another switch coming on. So the group of scientists are working on this idea in 1939. John Atanasoff, many of you have seen me wear my Iowa hoodie around class. He is a guy from Iowa State University. He's the American who created it, and then the German I was speaking about earlier named Konrad Zuse. Like these guys simultaneously are given credit for inventing the computer. Conrad here invented the Z3. This is an electrical mechanical computer, essentially the world's first working programmable computer, fully automatic digital computer, that is. The Z3 was built with 2,600 relays, implementing a 22-bit word length that operated at a clock frequency of about 4 to 5 hertz. That is really slow compared to what you guys know a computer can operate now. My lab computers are currently at 3 gigahertz. Now the code for this computer was stored on punched film, and the initial values of variables had to be entered manually. And here's just an interesting quote from Conrad. He said, "The dangers of computers becoming like humans is not as great as the dangers of humans becoming like computers." All this AI freaking out stuff that people are doing is essentially nonsense when you put it into that context. Okay, so I used to be a history teacher. I need to calm down on the history here. The reason we're going to say these two guys are the guys who invented the computer and not any of the other people is because of the concept of this electrical storage thing. When we learned in class what a computer is, we used 4 qualities to say that a thing must have in order to get that name, a computer. So as a review question here, what were those 4 things? If you don't remember, I'm not going to be cruel and ask you to Google it. It is basically a thing needs input, output, storage, and processing to be considered a computer. Now, the storage part was always tricky to me because on RAM, RAM is storage, and if something is stored for like a microsecond, are we going to still say it's a computer? And if you're thinking of this mechanical computer, well, where's the storage in that? Well, this right here was the storage. So here's the storage. The input is turning the gear, maybe setting the values. Turning the gear is the input, and the gear itself is the processor. And then the output is the numbers that result after you've turned the gear, after you've processed. To learn more about this, a great video on YouTube by Computer File called The Analytical Engine would be worth your time to watch. In that video, the man mentions that this is all before a guy named Faraday would start on his work on electromagnetism. So like Faraday is just another big name in early computing. So that analytical and difference engine is just too complicated for me to break down in a short video. I will show you a small clip of what I think is the best way to think of a gearbox working. So right here really helped me understand what the machine was doing. So basically you can have 2 numbers like 3 and 4 and they add up to 7. And because of the way these gears are placed next to each other, if I let those gears move, every number is a combination that can be added together to make 7. So 1 plus 6, 7. If it keeps going, 7 plus 0, 7, right? So it gets way more complicated, but for the sake of this video, that's how we took gears and the data right there on the gears, and we turned that into the ability to look at many different equations, all through the processing power of that lever that you use to turn the gears. To summarize, computers are all about turning patterns and chain reactions into a specific type of output. If you want another visual like that one with the gears to wrap your mind around these chain reactions I'm talking about, try YouTubing this Programming with Dominoes by a guy named Stand Up Maths. Really interesting videos to see essentially what computers are doing at the microscopic level. Ada Lovelace had a special position in history because she was the first to recognize that a machine had applications beyond pure just calculation. We don't need to build these giant machines to just do calculation. We could do other things. She published the first algorithm intended to be carried out by such a machine. And as a result, she is sometimes regarded as the world's first programmer. So let's talk a little bit about memory and how that relates to programming. Basically, you have three types of memory. You have the registers, which are literally on the CPU, so they're right next to the processor. And because they are physically close to the processor, the speed in which that processor can access the memory is extremely high. Now, the size of it is very low. Right here, you see something called an instruction register. This is only 8 bits. Now, this is just a built from the ground up computer by a guy named Ben Eater, another video series I suggest you watch. But registers have a very low capacity. Then when you move into RAM, you're going to get a medium level of speed and medium level of capacity. But when you get to the hard drive, the thing that you can like download stuff on and carry around, well, the speed of accessing that data is low. To just stare at this a little bit, what you're able to do with all these interconnecting wires, these connections that exist, you can have something like an instruction register where using this permutation of 0, 1, 0, 0, maybe 0, 1, 1, 1. I don't know why the colors were different here. I'm positive there's a reason, I just don't remember it off the top of my head. Well, this is a very specific instruction that the computer is getting to then look into register B with this permutation 0, 1, 0, 0, 0, 0. So this is the data that has some sort of meaning that the computer knows. So the instruction is going to manipulate the data to have this output of 128, it looks like. I don't know if this was a simple addition thing, so maybe the instruction is like add two numbers. Oh, and since I know my binary, we're doing 1, 2, 4, 8, 16, 32, 64 here. If this is 64, what number, if this was add, the instruction to just add 64 to something else to make 128, what would that number be? So it must also be connected to another register, so those two registers combined can have this output. So it's interesting for me to tell you that the keyboard and mouse are your primary inputs to get these chain reactions to occur. And we have everything from videos to social media to amazing games because of that. And it really is just that simple. Setting up the chain reactions are not simple at all. But the idea that the computer is only doing these things, getting input, storing it, processing it, and then outputting it, that's all there is to it. So try to do this without looking. What's the difference between a hard drive, RAM, and registers? Now let me tell you a little bit more about the process. Basically, when you write a program, you're taking patterns of ones and zeros, right? Those permutations that matter. Permutation is an order that matters. So you're taking these switches and turning them on so that other switches can come on in just the way you want. So you take these patterns. These instructions are used to tell the computer what to do with some of the data that is already stored on the machine. So you have patterns that make up instructions, and you have patterns that make up data. And I suppose using the definition of pattern loosely here, what I'm saying is every time you get like 0, 1, 0, 0, 0, 0, you know what the outcome is. And at the very lowest level, the instructions and data, they are encoded with a certain pattern. So 65, the binary that makes 65, the binary that makes A is 65, and then 66 is B, and so on. And another thing that blew my mind when understanding programming is like, think of that turtle programming we did with JavaScript. All you're doing is giving the computer instructions to move this data, this picture of the turtle, to another point on the monitor, which is this XY coordinate system that we use. Like those are the numbers that you give the turtle to then move. But is he really moving? No, the pixels are turning off and on in a certain way to make it look like movement. But that's just those low-level instructions, these things that you don't really have to care about when you're at the high level. So when you're at the high level, how does a computer know what those pixels are to turn off and on and change the colors of? The computer figures these things out through either an interpreter or a compiler. Now, an interpreter is similar to a compiler. They both are in charge of translating your code, your programming, your high-level language into what's called machine code. So it's those ones and zeros. But interpreter is a little bit easier to wrap your mind around because an interpreter is working like step by step. So you put in some code, the interpreter goes through it, and you can see what is processed out. So the compiler is taking all those words that you use to come up with a program and then turning it into the machine code there for the processor to work through and then have a result. So this one is a bit time consuming, but the good news about it is compilers are often faster once all done, but it's slower to create or develop the program in the first place because you have to do everything, you have to compile everything at once. An interpreter is more like line by line. And just like in the beginning of the lesson where we had procedural languages and object-oriented languages, we can also use these other words and categorize languages into these other categories because of that. C and C++ are both compiled languages, though C is procedural and C++ is object-oriented. There's another word you should know, an assembler. So all of these are very similar to each other, but for the sake of this lesson, just know that there is a translator. This is a thing. This is a program. So get it, code that creates code or helps translate code into ones and zeros. These are the programs that do that. We're taking your letters and numbers you typed out into a text editor, assumably, turning it into sequences of ones and zeros, and again, not even ones and zeros. They're turning those words into these patterns of electricity on and offs that the computer understands and can do stuff with, or at least create a predictable output for us. If you really want to dig down into this, I suggest that Ben Eater video. Like, here is the computer he built from just these rectangles full of transistors, thus creating logic gates connected by wires. And he can take his hand and set the registers or set the instruction register to whatever he wants and get a predictable output right here. It's pretty impressive. So think back to the drawing while blindfolded activity we did in the beginning of the lesson. Would you have liked the person with the blindfold to have heard you say all your instructions, think about all those instructions, and then execute what you said? Or would you like them to listen to you and step by step do the thing you say, and during each step you have a chance to look at what they're drawing and then make a change if you feel it's necessary? Like, whatever you answer for those two different approaches to giving instructions, we're basically talking about a compiled language versus an interpreted language. Again, pros and cons to doing it this way. For me, my answer depends on the person I'm giving instructions to. For the computer programmer, I don't think it's that simple. They're not making that decision based on the hardware they're working on. They're making that decision based on a lot of other factors, including just their own limited knowledge. Some people know how to program in Java, and like, that is it. They don't study any other language. So we'll end this lesson on what I think is a pretty fun activity. If a compiler is difficult to test but runs quickly, and an interpreter is easy to test but typically runs slowly, which one of these scenarios would need a compiler versus a interpreter? Think about the first one. You're programming a rocket to take some humans to the moon. What are you going to use, an interpreter or a compiler? Second example, what if you're programming a school's website to display important information to parents? Which language do you go with, a compiled one or an interpreted one? And your last one, creating an application to allow teenagers to send video clips to each other. That sounds very familiar. I think someone has programmed that before. So take deep breaths here. Again, the point of the lesson was just to get people feeling more comfortable with programming languages and hopefully not freaking out too much. There's so much more to learn about this process, but for today, that's our lesson. An eagle's eye view of how switches are activated in a computer through either magnetism, like your finger on a touchscreen, or keys on a keyboard, or the laser in a mouse. These things are causing changes to data, which causes changes to the output that you are experiencing. Here's my DOL. Please describe how we go from high-level languages to the computer utilizing Boolean logic. And here's my overarching analogy. To succeed in both Kung Fu and programming, you have to do things in a very repetitive and balanced way to succeed.